Hello and welcome to Mysteries of Earth. Today we confront one of the most mind-bending questions in all of science, if nothing exists outside the universe. What is it expanding into? For generations, we imagined the universe as a vast stage with stars scattered across it. But what if the stage itself is stretching, creating more room as it grows? From the mysterious force of dark energy to the echoes of the Big Bang hidden in cosmic radiation, the truth about expansion defies common sense and shatters our everyday understanding of reality. In this video, we'll journey from the first moments of inflation, when the universe grew faster than light, to the discovery of the cosmic microwave background, to the unsettling idea that our cosmos may be just one bubble in an endless multiverse. If you enjoy exploring science, mystery, and the unknown, make sure to subscribe to Mysteries of Earth and join us as we uncover the secrets of the expanding universe. What does it mean to say that the universe is expanding? It sounds like such a simple idea. We know what expansion looks like. A balloon grows as air rushes in. A drop of ink spreads when it touches water. A city sprawls outward into the land around it. Expansion, in every example we know, requires a container, a surrounding space into which something grows. So naturally, when we're told that the universe itself is expanding, the question arises like a riddle we can't escape. If the universe is growing, what is it growing into? It seems like a question with an obvious answer. And yet, it is one of the most deceptive questions ever asked. Because the universe is not like a balloon. It is not like an explosion scattering shrapnel into empty air. It is not even like a city reaching into its countryside. It is something far stranger. The universe, by definition, is everything. All space, all time, all matter, all energy. There is nothing outside it, because outside is a concept that only exists within space. Asking what the universe expands into is like asking what lies north of the North Pole. The question dissolves the moment you examine it. And yet, the question won't let us go. Because when we look up at the night sky, we see evidence everywhere that space is stretching. Galaxies are racing away from us. The further they are, the faster they move. The very fabric of reality is swelling, and so our minds insist it must be expanding into something. This paradox, so simple yet so impossible, is where our story begins. To understand it, we must first strip away the metaphors that bind us. When we imagine an explosion, we picture fragments racing outward through an empty void. But in the case of the universe, there is no void outside to race into. Instead, space itself is growing. It is as if the stage on which the play of existence unfolds is continuously building itself, adding more floorboards, stretching its boundaries, creating more room for the actors as the play goes on. Cosmologists often turn to analogies to help us imagine this. One of the most famous is the balloon. Picture dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther and farther apart. Each dot is like a galaxy. None of them are traveling across the surface. Rather, the surface itself is expanding, carrying them away from one another. But this image contains a hidden trap. The balloon's surface is embedded in a larger space. The air around it, the three-dimensional room in which it inflates. Our minds can't help but imagine the universe in the same way, expanding into some larger arena. Yet that arena doesn't exist. The universe is not a balloon in a room. It is only the surface, with no outside at all. Another analogy comes from raisins in a loaf of rising bread. As the dough expands, each raisin grows farther from the others. From the perspective of any single raisin, it seems as if all the others are rushing away. Again, it is the dough, the space itself, that grows. There is no need for an outside container. But here too the analogy fails if we take it too literally. Because real bread expands into an oven, the universe expands only into more universe. This is where our everyday intuition betrays us. Our lives are spent in a world of objects moving through space. We have never experienced space itself changing. It is so far beyond our senses that even when told it is happening, our minds twist it into familiar shapes, balloons, explosions, waves rushing into emptiness. Yet the universe resists these images. It refuses to fit inside them. When Albert Einstein first wrote down the equations of general relativity, he discovered something extraordinary. Space and time are not passive backdrops for the universe. They are dynamic. They can bend, twist, and ripple. They can expand. It was a Russian mathematician, Alexander Friedman, who first solved Einstein's equations in a way that allowed for an expanding universe. Later, Georges Lemaitre, a Belgian priest and physicist, proposed that our universe had once been smaller, denser, perhaps originating in what he called a primeval atom. The idea sounded outrageous. Even Einstein himself dismissed it at first. But in 1929, Edwin Hubble P. read through his telescope and saw the proof. Galaxies were fleeing from us, their light stretched to longer, redder wavelengths. The further away a galaxy was, the faster it receded. Space itself was stretching, carrying galaxies with it. For the first time in history, humanity was forced to confront the staggering truth. The universe was not static. It was growing. But what then was it growing into? The answer, the one physics has returned to again and again, is that it expands into itself. The universe does not need an outside. As it expands, it creates new space, new distance, new room for itself to exist. The paradox remains unsettling. Our language seems inadequate to capture it. We can describe what the equations tell us, but when we try to wrap our imaginations around it, we always end up smuggling in some hidden outside that doesn't exist. And this is where philosophy enters. The question of expansion is not only a scientific puzzle, it is a challenge to how we think about existence itself. For millennia, humans imagined the cosmos as something finite, perhaps a dome of stars, perhaps a system of crystalline spheres, something bounded, contained, with a beyond. To accept a universe with no outside at all is to step into a realm where our categories of thought begin to fail. What does it mean to say that expansion has no destination? That it does not unfold into emptiness, but creates its own arena as it grows? These are not merely technical puzzles of physics. They are invitations to reimagine what it means to exist, what it means to be inside anything at all. And so we return to our impossible question. If the universe expands, what is it expanding into? The honest answer is nothing. Not because it expands into emptiness, but because emptiness itself is a concept that only exists once space exists. Expansion creates the very framework in which into has meaning. It is not an answer meant to satisfy, it is an answer meant to transform the way we see the question itself. This is the beginning of our journey. In the chapters to come, we will travel through the strange landscapes of cosmology. We will confront the mysteries of inflation, the enigma of dark energy, and the haunting possibilities of multiverses. We will ask what happens when expansion never ends, and what it means for memory, meaning, and our place in the cosmos. But before we can go there, we must first sit with this paradox, right? The one that unsettles our most basic intuitions. The universe expands. It expands not into something else, but into more universe. And with that, the impossible question becomes not a barrier, but an opening, a doorway into the deepest mysteries of reality. In the early years of the 20th century, the universe seemed simple, or at least it appeared to be contained. Astronomers believed the cosmos consisted of a single great island of stars, the Milky Way. Beyond it, perhaps, nothing. Or if there was something, no one could say for certain. Scattered across the night sky, however, were strange smudges, faint ghostly clouds known as spiral nebulae. Some argued they were simply gas and dust within our own galaxy. Others suspected they might be something far more extraordinary, entire star systems in their own right, unimaginably distant. It was a question without proof, debated fiercely in lecture halls and observatories. But in 1929, one man standing high on the slopes of Mount Wilson in California would shatter humanity's understanding of its place in the cosmos. His name was Edwin Hubble. Hubble was not what most imagined a scientist to be, a former lawyer, an athlete, a man with the presence of a soldier and the patience of a monk. He had traded the courtroom for the telescope, law books for star charts. And from the 100-inch Hooker telescope, the largest in the world at the time, he gazed into those mysterious spiral nebulae. What he found would change everything. By examining the light from these nebulae, Hubble measured tiny shifts in their spectral lines. This was the phenomenon of redshift. When an object moves away from us, its light stretches into longer, redder wavelengths. To Hubble's astonishment, nearly every spiral nebula he studied was redshifted. They were not only distant galaxies beyond the Milky Way, they were receding from us. And not just receding. The further away a galaxy was, the faster it seemed to flee. It was a pattern no one had expected, a law written into the heavens themselves. Today we call it Hubble's law. The velocity of a galaxy's recession is proportional to its distance. In other words, the universe is expanding. Imagine the shock of this discovery. For centuries, humans believed the cosmos was static, eternal, unchanging, an endless stage on which stars played out their lives. But here was proof that the stage itself was in motion. Galaxies were not frozen lanterns suspended in the dark. They were islands adrift on a sea that was swelling, carrying them farther apart with every passing moment. The universe, it turned out, was not a quiet cathedral. It was a restless ocean. Of course, such a revelation was difficult to grasp. How could space itself expand? How could galaxies move away without any center, without any edge? To make sense of it, scientists reached for analogies. One was the balloon, picture dots drawn on its surface. As the balloon inflates, every dot grows farther from every other. No single dot is the center. To each it seems as if all others are rushing away. That is our universe. We are not watching galaxies fly through emptiness. We are watching space itself stretch. Another analogy was a rising loaf of bread. The raisins scattered throughout the dough grow farther apart as the dough expands. The loaf has no edge that the raisins move toward. Instead, the dough itself grows everywhere, all at once. These images, simple yet profound, help us glimpse what Hubble's discovery truly meant. Not just that the cosmos is vast, but that it is alive with motion on the grandest of scales. At first, even Einstein resisted the idea. His equations of general relativity had allowed for the possibility of expansion, but he had dismissed it, introducing what he called the cosmological constant to hold the universe still. When he saw the evidence of galaxies in flight, he reportedly called that constant his greatest blunder. But Hubble's evidence could not be denied. The universe was not static. It was growing. It had a past. And if it was expanding now, then logic demanded it must once have been smaller, much smaller, perhaps staggeringly. It had once emerged from a single, incomprehensibly dense state. The seeds of the Big Bang theory were planted. Yet Hubble himself remained cautious. He was a man of data, not speculation. He rarely ventured into philosophy, but whether he admitted it or not, his work had torn open the fabric of human thought. No longer could we imagine ourselves at the heart of a small, bounded universe. We were adrift in a cosmos filled with galaxies beyond counting, each retreating into the distance. And the further we looked, the faster they fled. It was as though the universe itself was running away from our gaze, always offering us more mystery the further we reached. Today, Hubble's discovery is considered one of the greatest scientific revolutions in history. It redefined cosmology. It gave us a universe with a beginning and, perhaps, an end. It set us on the path to modern astrophysics, to dark energy, to inflation, to the profound questions we still wrestle with today. And it also did something subtler, something more human. It humbled us. For thousands of years we thought of the stars as a distant but comprehensible dome above our heads. Now we know they are part of a grander structure, one so vast that our own galaxy is just a speck among trillions. To stand beneath the night sky after Hubble is to see, not a sea, isling, but an infinity that is still unfolding. The paradox we explored in our first chapter, the question of what the universe expands into, now takes on even greater urgency because Hubble gave us the undeniable evidence that expansion is real. But he left us with an even greater mystery. What drives it? Why does space stretch? Why does the universe not only grow, but accelerate in its growth? And what does this expansion mean for the ultimate fate of everything we know? These were the questions that scientists began to ask in the wake of Hubble's astonishing discovery, questions that would lead to debates over dark energy, cosmic inflation, and the very destiny of the cosmos itself. And so, from a telescope on Mount Wilson, gazing at faint smudges of light, humanity stepped into an era of wonder and bewilderment, one that continues to this day. Because the night sky is no longer just a map of stars, it is a story in motion. And we are still learning how to read it. In science, mistakes are often just as important as discoveries. A wrong turn can illuminate the hidden path. A false assumption can reveal the truth when it collapses, and sometimes a blunder by the greatest mind of all can become the key to solving the deepest mystery of the universe. Albert Einstein once called something he had done his biggest mistake. But time has a strange sense of irony. Because today, that so-called blunder may be the single best explanation for why the cosmos is expanding faster and faster with every passing moment. When Einstein completed his general theory of relativity in 1915, he had reshaped physics. No longer was gravity a mysterious force acting at a distance, as Newton had described. Instead, it was the bending and warping of space-time itself, a cosmic geometry that responded to the presence of mass and energy. Einstein's equations were powerful. So powerful, in fact, that they could describe the entire universe at once. But when he applied them to the cosmos, they gave him an unsettling result. The math showed that the universe could not sit still. It must either expand or contract. To Einstein, this was absurd. The consensus of his time was that the universe was static, eternal, unchanging on the largest scales. Philosophers had imagined it that way for millennia, and astronomers had no evidence to suggest otherwise. So Einstein did what few would dare. He changed his equations. He introduced an extra term, a kind of mathematical patch, to counteract the unwanted motion. He called it the cosmological constant, symbolized by the Greek letter L, lambda. The cosmological constant acted like a repulsive force, an anti-gravity that balanced the attractive pull of matter. With it, Einstein could freeze the universe in place, keeping it static and eternal, perfectly in line with the worldview of his era. For a time it worked. The equations no longer demanded expansion or contraction. They allowed a universe that simply existed, timeless and still. Einstein had preserved the cosmos as people believed it must be, but the universe does not bend to our assumptions. In 1929, Edwin Hubble's observations of distant galaxies revealed the undeniable truth. Space was expanding, the very thing Einstein's math had first predicted. The thing he had tried to erase turned out to be real. Einstein reportedly called the cosmological constant his greatest blunder. He had had the truth in his hands, and he had let it slip away. Instead of trusting his equations, he had forced them to fit his expectations. And for that, he missed the chance to predict one of the most profound discoveries in all of science, the expansion of the universe. It is a humbling story. Even the greatest scientist of the 20th century, perhaps of all time, was not immune to the weight of human bias. Einstein's brilliance gave him the keys to the cosmos, but his intuition, shaped by centuries of belief in a static universe, led him to lock the door. And yet, the story does not end there. Because the cosmological constant, that discarded patch, that supposed mistake, has returned in the most astonishing way. Fast forward to the late 1990s. Astronomers measuring distant supernovae expected to see evidence that expansion was slowing down. After all, gravity should pull galaxies back together over time, but instead they found the opposite. Expansion was not slowing, it was accelerating. Some hidden energy woven into the fabric of space itself, was pushing galaxies apart with growing force. The culprit? We call it dark energy. And the simplest way to describe it is to bring back Einstein's forgotten term, the cosmological constant. Had once been a patch to freeze the universe. Now it was reborn as the very thing, driving its runaway growth. This irony is almost poetic. Einstein's blunder might be the clue to the greatest mystery of modern cosmology. Roughly 70% of the energy in the universe appears to exist in this invisible form, dark energy, behaving exactly as his constant predicted. A uniform, repulsive pressure embedded in space itself, causing the expansion to accelerate without end. It is as though the universe itself remembered what Einstein had tried to erase. Of course, the true nature of dark energy remains unknown. Is it really a cosmological constant, an intrinsic property of space, present everywhere and unchanging through time, or is it something more exotic, like a dynamic field that evolves as the universe grows? We do not yet know, but what we do know is that Einstein's equations, once adjusted to fit human expectations, now stand as the most faithful description of reality we possess. The cosmological constant, born as a mistake, may turn out to be the most accurate insight of all. There is a lesson here, one that reaches beyond physics. The universe is under no obligation to conform to our intuitions. Often, the truth lies in the very things we dismiss. The strange terms in the math, the possibilities that feel absurd, the answers that seem to contradict our instincts. Einstein himself learned this lesson with humility, and, perhaps, so must we. The cosmological constant began as a desperate correction to hold the universe still. But today, it points us toward the realization that the cosmos is not just expanding, it is doing so with a mysterious and unstoppable force. And that realization brings us to the next great puzzle. If the universe is accelerating, where does it lead? Does expansion go on forever, carrying galaxies beyond sight until the night sky is empty? Does it tear space apart in a catastrophic big rip? Or does some hidden balance await us in the far future? In the wake of Einstein's so-called blunder, we are left with a deeper, more haunting question. Not just why the universe expands, but what its expansion ultimately means. And to answer that, we must look not only backward to the origins of space itself, but forward to the long, uncertain future that expansion holds in store.
How do you measure the immeasurable? How do you place a ruler against the sky? When we gaze into the night, stars and galaxies scatter themselves across a seemingly flat dome of blackness. They shine with different intensities, but brightness is no guide to distance. A nearby candle may flicker faintly, while a lighthouse farther away blazes like a star. Light alone cannot tell us how far away its source truly lies, and yet, if we wish to understand the universe, its size, its age, its fate, we must learn to measure the distance to the stars. Astronomy is, at its heart, an act of measurement. And to reach across billions of light-years, astronomers have built what they call the cosmic distance ladder, a series of methods, rung by rung, each one extending farther than the last. The first rung is deceptively simple. Parallax. Hold out your thumb at arm's length. Close one eye, then the other. Watch how your thumb seems to jump against the background. This tiny shift is parallax, the effect of observing from two slightly different positions. Astronomers use Earth's orbit around the Sun in the same way. By measuring how a nearby star appears to shift against the more distant background over the course of 6 months, they can calculate its distance through geometry alone. Parallax is the only direct measure we have of stellar distance, but it works only for stars relatively close, within a few thousand light-years. Beyond that, the shift becomes too small to detect. The ruler of parallax is powerful, but it does not reach far, and so astronomers step to the next rung. Enter the Cepheid variable stars. These are stars that pulse with astonishing regularity, swelling and dimming in cycles that can last days or weeks. In the early 20th century, Henrietta Swan Leavitt discovered a remarkable pattern. The brighter a Cepheid star truly is, the longer its cycle of.
And then, at the farthest rung, lies the oldest light of all, the cosmic microwave background. This faint glow, discovered in 1965, is the afterglow of the Big Bang itself. It comes to us from a time when the universe was only 380,000 years old, when atoms first formed and light could travel freely through space. The cosmic microwave background is not measured by brightness alone. Instead, it carries within its faint ripples a map of the infant universe, tiny fluctuations that tell us about its density, its composition, and its overall geometry. From this, cosmologists can infer the scale of the entire cosmos and calculate the rate of its expansion billions of years ago. It is the farthest and most profound rung of the ladder. Beyond it, we can see no further. Beyond it lies only the mystery of what came before. But here, on the rungs of this great ladder, a new puzzle has emerged, one that strikes at the heart of cosmology. When astronomers use nearby methods like Cepheids and supernovae, they calculate the expansion rate of the universe, the Hubble constant, to be about 73 kilometers per second per megaparsec. But when they use the cosmic microwave background, the value comes out lower, about 67 kilometers per second per megaparsec. This discrepancy is known as the Hubble tension, and it is not small. The gap is far larger than any expected error. It suggests that something fundamental may be missing in our understanding of the cosmos. What does this tension mean? Perhaps our models of the early universe need revision. Perhaps dark energy is not constant, but evolves with time. Perhaps there are hidden particles, new physics waiting to be discovered, woven into the first moments after the Big Bang, or perhaps, like Einstein a century ago, we are still forcing the universe to fit our assumptions when the truth is stranger than we dare to imagine. The cosmic distance ladder is one of humanity's greatest achievements. With nothing but geometry, patience, and light itself, we have stretched our reach from the stars nearest our sun to the edge of time. Each rung represents generations of observation, discovery, and persistence, but the ladder is not complete. Its uppermost rungs are still uncertain, and the tension between them may yet reveal a revolution in physics, one that changes how we see the origin, the expansion, and the destiny of all that exists. The universe expands, that much is clear. But how fast, and why? To answer those questions is to confront not only the history of the cosmos, but its future. Will it expand forever into a silent darkness? Will it slow and collapse back into fire? Or will dark energy continue its inexorable push, tearing space itself apart? As we climb the cosmic distance ladder, we look not only backward in time, but forward, toward the ultimate fate of everything we know. And in that pursuit, we step into the next chapter of our journey, to trace the universe's expansion into the deep future, where the answers to its destiny may lie waiting. How do you measure something that has no edge? How do you describe the growth of a universe that is not expanding into anything, but expanding itself? The answer lies in mathematics, and the key to it all is a simple function, one symbol, quietly powerful, the scale factor. Physicists call it ART. It is not a distance or a velocity or a size, it is a ratio, a measure of how big the universe is at any moment in time compared to how big it is now. At the birth of the universe, AT was almost zero, a cosmos compressed into a fireball of unimaginable density. Today, AT is defined as 1. Tomorrow, it will be greater than 1. In the far future, it may stretch toward infinity. The scale factor is like a clock, but not of hours and minutes. It is a cosmic heartbeat, recording the rhythm of expansion itself. This simple function allows us to connect light, distance, and time in one sweeping story. Every galaxy we see carries with it the imprint of expansion, written in the form of redshift. Light stretches as space stretches. A wave that left a galaxy billions of years ago arrives today longer, redder, shifted by the growth of the cosmos. The greater the redshift, the farther back we are looking. The higher the stretching, the smaller the scale factor when that light was first released. When we measure redshift, we are not just looking across distance, we are looking back through the history of expansion itself. By gathering these measurements, cosmologists reconstruct the entire timeline of the universe. They plot the growth of AT against cosmic time. And what emerges is a story filled with twists and turns. For billions of years after the Big Bang, expansion was slowing down. Gravity, pulling on matter, resisted the outward push. Galaxies and clusters began to take shape in this era, their seeds planted in the tiny ripples of the early universe. Then something shifted. Roughly 5 billion years ago, expansion stopped decelerating and began to accelerate. A mysterious energy, hidden in the fabric of space itself, overtook gravity's pull. Dark energy seized control and the growth of AT began to speed up. This turning point is the single most important clue to the universe's fate. For the scale factor is not just a measure of the past, it is also a prediction of the future. If the acceleration continues, as observations suggest, then a T will grow without bound. Galaxies will drift apart until only the faint glow of local stars remains. Expansion will push everything beyond reach. This is the path of the Big Freeze, a universe that grows colder, emptier, and darker as time stretches toward eternity. But mathematics leaves room for other possibility. If dark energy is stronger than we think, if it increases with time, then expansion could accelerate without limit, tearing galaxies, stars, planets, and even atoms apart. This apocalyptic scenario is called the Big Rip, a future where even space-time itself is undone. And if, against expectation, dark energy were to fade or reverse its sign, gravity could regain control. Expansion could slow, halt, and then collapse into a fiery implosion, the Big Crunch, the mirror of the Big Bang, a universe ending as violently as it began. All of these possibilities are written in the mathematics of the scale factor. The fate of the cosmos is not decided by myth or philosophy, but by the precise curve of a T through time. And yet, for all our equations, there remains a deep unease. The numbers are incomplete. We do not know what dark energy truly is. We do not know why it appeared when it did. We do not know whether it will remain constant forever or shift into something stranger. The universe is telling us a story, one we can follow with elegance through mathematics, but its ending is still missing. There is something profoundly humbling about this. In the scale factor, we have a tool of immense clarity, a simple ratio that charts the growth of everything. But clarity does not mean certainty. The mathematics can describe the possibilities, but it cannot yet choose among them. And so we find ourselves suspended between futures, a frozen eternity, a catastrophic rip, a violent collapse, or perhaps something entirely unforeseen. The only way forward is to measure, again and again, with greater precision, to listen more closely to the whispers of galaxies and the stretched light of the cosmos, to map the curve of a T until it reveals which path we walk. The scale factor is more than a function. It is the unfolding of existence itself. Every moment of expansion, every red-shifted photon, every breath of cosmic history is encoded within it. It is a reminder that the universe is not a static stage, but a living, changing entity, one whose story is still being written. And as we trace that story, we move closer to the ultimate question, not just how the universe grows, but how it will end. For the mathematics of expansion leads inevitably to the mathematics of destiny. And so, as we close this chapter, we look to the horizon of time itself. Beyond the redshift, beyond the accelerating curve of a T, beyond the familiar possibilities of freeze, rip, or crunch. What does the future hold in the long-distant epochs when stars die and galaxies fade? Can intelligence survive such vast stretches of time? Can consciousness find a place in the deep silence of eternity? These questions draw us onward into the final mystery, the long future of the universe and the ultimate fate of everything we know. In the late 1990s, astronomers gazed deep into the cosmos and found something that should not have been possible. They were studying supernovae, exploding stars so bright they can outshine an entire galaxy for a brief moment in time. These brilliant deaths of stars serve as standard candles, cosmic beacons whose intrinsic brightness is known. By comparing their true brightness to how faint they appear from Earth, astronomers can calculate their distance with remarkable precision. The goal was simple: to measure how the expansion of the universe was slowing down under the pull of gravity. But what they discovered shook the foundations of cosmology. The universe was not slowing down at all. It was speeding up. This revelation seemed impossible. For decades, the assumption had been that gravity, the universal attraction of all matter, would gradually decelerate the expansion. Perhaps it might slow forever, leaving a cold, static cosmos. Perhaps it would eventually reverse, collapsing the universe into a fiery Big Crunch. But never did scientists expect to find acceleration. Yet the data was clear. Distant supernovae were fainter than expected, farther away than they should have been if expansion was slowing. Something was pushing galaxies apart with ever-growing speed. Something hidden, powerful, and utterly mysterious. They called it dark energy. What is dark energy? Even today we don't know. The simplest idea is that it is the cosmological constant, the very same term Albert Einstein once introduced and later discarded as his greatest blunder. A constant energy density built into the fabric of space itself. A kind of pressure that does not dilute as the universe expands but remains steady, exerting its influence everywhere and at all times. If this interpretation is true, dark energy is simply the cost of having empty space. Even when all matter and the radiation is stripped away, the vacuum itself still hums with energy, a quiet background presence that drives the cosmos apart. But there are other possibilities. Perhaps dark energy is not constant but dynamic, a field that evolves over time, waxing and waning like tides we have yet to chart. Such a field might decay in the future, causing expansion to slow once again, or it might grow stronger, accelerating expansion until the very fabric of space-time is torn apart. And then there is the most profound possibility of all, that dark energy is not a substance or a field, but a sign that our understanding of gravity itself is incomplete. That Einstein's equations, magnificent as they are, might not be the final word on how space and time behave on cosmic scales. Whatever its nature, dark energy dominates the universe. Today, matter, everything made of atoms, stars, and galaxies, accounts for less than 5% of the cosmos. Dark matter makes up about a quarter, and the rest, nearly 70%, is this invisible force of acceleration, dark energy. We live not in a universe ruled by matter, but in one ruled by emptiness. This realization brings us to a sobering question. What does dark energy mean for the future of everything? If it remains constant, the universe will continue expanding forever. Galaxies will drift beyond the horizon of visibility, stars will fade, black holes will evaporate, and the cosmos will approach heat death. A silent eternity where nothing new can ever happen. If dark energy grows stronger, the universe may end in a big rip. Expansion will accelerate until galaxies are torn apart, stars shredded, planets dissolved, even atoms ripped into their constituent particles. In this fate, space itself is destroyed in a final act of violence. If dark energy weakens, gravity might one day regain control, pulling everything back in to a collapse. The universe would end in fire, a big crunch that could just possibly give rise to a new Big Bang, a cosmic rebirth. The truth is, we do not yet know which of these paths we are walking. But perhaps the greatest mystery of dark energy is not what it is or where it leads, but why now? Cosmologists call this the cosmic coincidence problem. For most of history, the universe was dominated by radiation, then by matter. Dark energy only became significant within the last few billion years, the very same epoch when life emerged on Earth and intelligence began asking questions about the cosmos. Why should acceleration begin now, just as we are here to witness it? Is this a coincidence or a clue? Some suggest it is merely chance, a lottery of cosmic timing. Others wonder if there is a deeper principle at play, that perhaps intelligent observers can only arise in universes where dark energy appears at just the right moment. Still others question whether the multiverse itself might explain this strangeness, countless universes with countless expansion histories, and we simply live in one where the conditions align for us to exist. Whatever the explanation, the question lingers, unsettling and profound. What is it about our moment in cosmic history that makes it so finely balanced? Dark energy forces us to confront not only the fate of the universe, but also the fragility of knowledge itself. We live at a time when the expansion is measurable, when galaxies still shine, when the cosmic microwave background still whispers its story of beginnings. But in the far future, accelerating expansion will erase these clues. Galaxies will vanish, the background radiation will fade, and the universe will appear static and eternal to any civilizations that may still exist. We are the fortunate few who live in the brief window when the cosmos reveals its true nature. And so dark energy stands as both a mystery and a gift. A mystery because it defies explanation, a gift because it has grantee, does the chance to glimpse the vast, unfinished story of the universe. In its pull, we see our future. In its timing, we sense our precarious place in the grand design. And in its strangeness, we find the humbling reminder that reality is deeper than our imagination, stranger than our language, and more wondrous than our science has yet revealed. The expansion is not done. The universe is still unfolding, still writing its future in the mathematics of space and time. Dark energy is its pen, sketching destinies we cannot yet predict. But the question remains, does expansion truly mean dissolution? Or might there be deeper structures hidden in the fabric of reality, structures that ensure nothing is ever lost, not even in the silence of eternity? To answer this, we must turn to the paradox of information itself. For if the universe expands forever, what happens to the memories, the patterns, the stories that define us? This is where our journey leads next, into the strange connection between cosmic expansion and the fate of information. When we look at the night sky, we like to think we're seeing the universe as it truly is. Stars burning, galaxies shining, nebulae glowing with cosmic fire. But what if the most important part of the universe is the part we cannot see? This unsettling truth began to emerge in the mid-20th century when astronomers turned their telescopes toward galaxies and began measuring how they moved. What they discovered has haunted cosmology ever since. In the 1970s, Vera Rubin and Kent Ford studied the rotation curves of spiral galaxies. According to Newtonian mechanics, stars orbiting near the edge of a galaxy should move more slowly than those near the center, just as planets farther from the Sun orbit more slowly than Mercury or Earth. But the data revealed something impossible. The stars in the outer arms of galaxies were moving too fast. They were whipping around at speeds that should have torn the galaxies apart. By all rights, they should have flown off into intergalactic space, and yet the galaxies held together. The only explanation was that something invisible, some unseen mass, was providing the extra gravity to bind the galaxies together. Astronomers had stumbled upon the shadow of a hidden world, dark matter. Dark matter is not made of atoms, not made of protons, neutrons, or electrons. It does not shine or absorb light. It does not clump into stars or planets. It passes through us without notice, invisible, yet essential. And yet, by its gravitational pull, it shapes everything. Without dark matter, galaxies would not exist. Stars would never have formed. Even the Milky Way itself would have long since unraveled. This invisible substance makes up about 27% of the universe. Ordinary matter, everything we have ever touched, seen, or known, accounts for less than 5%. The rest is dark energy, the mysterious driver of acceleration. It is a strange hierarchy. Matter, we understand, is but a trace, while the unknown rules over almost all of existence. But dark matter is not just an accounting problem. It is central to the fate of the universe itself. Cosmologists speak of critical density, the precise balance between gravity and expansion. If the universe's density is above critical, gravity would one day halt expansion and pull everything back into collapse. If the density is below critical, expansion would continue forever, carrying galaxies beyond sight into eternal isolation. For decades, the great question was, which universe do we live in? Open, closed, or flat? Dark matter plays the deciding role. The more of it exists, the more gravity the cosmos contains. The less of it exists, the more expansion wins. When measurements were first taken, it seemed the universe might not have enough matter to reach critical density. But then came the discovery of dark energy, and the picture grew more complex. Dark energy accelerates expansion, while dark matter tethers galaxies together. The two are locked in a cosmic tug-of-war, their balance shaping the destiny of everything. And yet, in this delicate balance lies another riddle, the flatness problem. When cosmologists measured the geometry of the universe, they found it was astonishingly close to flat. Not curved inward like a sphere, not curved outward like a saddle, but balanced on the razor's edge of Euclidean geometry. For the universe to be so flat today, it must have been even more perfectly flat in its earliest moments. But why should the cosmos begin with such exquisite fine-tuning? A fraction of a percent deviation at the Big Bang would have led to a radically different universe, one that collapsed almost immediately, or one that expanded so quickly that no structure ever formed. And yet, here we are.
The leading answer to this puzzle comes from a bold and beautiful idea, cosmic inflation. According to inflationary theory, in the first sliver of a second after the Big Bang, the universe underwent a burst of exponential expansion. Space itself ballooned outward at unimaginable speed, smoothing out any irregularities and driving the cosmos toward flatness. Inflation not only explains the flatness problem, but also why the universe looks so uniform in all directions, and why tiny quantum fluctuations in the early universe seeded the galaxies we see today. But inflation also raises new mysteries. If space can inflate once, could it inflate again? Could it be inflating eternally, spawning an endless froth of universes, each with its own laws and constants? In solving one problem, inflation may have opened the door to the multiverse. Dark matter, dark energy, inflation. These are not just technical details of cosmology, they are signs that the universe is far stranger than our senses can perceive. We live inside a structure held together by invisible scaffolding, propelled by forces we barely understand and fine-tuned in ways that defy intuition. To ask about dark matter is to ask why galaxies exist at all. To ask about critical density is to ask whether the universe has a destiny. And to ask about flatness is to peer into the earliest instance of time itself, when everything we now see was compressed into a speck smaller than an atom.
We are left with the unsettling realization that most of the universe lies beyond our comprehension. The stars we see are just sparks on the surface of a vast, unseen ocean. The light we measure is only the echo of deeper forces. Our familiar atoms are the minority, ruled over by shadow and void, and yet it is this very mystery that draws us forward. For every riddle the universe presents, why galaxies spin too fast, why space accelerates, why geometry balances so precisely, is also an invitation to see more deeply, to think more daringly, to imagine more profoundly. The story of dark matter and critical density is not finished. New experiments are searching for the elusive particles that may make up this hidden mass. Telescopes are mapping the cosmic web with unprecedented detail, tracing the invisible threads of dark matter that bind the universe together. And theorists continue to wrestle with the questions inflation raises. Questions about whether our universe is unique or only one bubble in a cosmic sea. For now, one truth remains. The universe we see is only the surface of a greater whole. And in the shadows of dark matter and the mysteries of expansion, we are beginning to glimpse just how deep that whole may go. But this journey does not stop here. For if the early universe was sculpted by inflation, if dark matter binds galaxies, and if dark energy drives acceleration, then we must ask, what are the ultimate consequences of these forces? Where does expansion lead when carried forward not for billions, but for trillions of years? That is the question we now face. as we turn from the present mysteries of cosmology to the long, unfathomable future of the universe itself. When we ask, what is the universe expanding into, we often imagine some vast emptiness, a void beyond the stars. But what if the answer is even stranger? What if our universe is not the whole story at all, but just one bubble, floating in an endless cosmic sea? This is the vision suggested by one of the boldest ideas in modern cosmology, eternal inflation. The theory begins in the earliest fraction of a second after the Big Bang. According to inflation, the newborn universe expanded at unimaginable speed, ballooning outward so fast that the observable cosmos grew from smaller than an atom to larger than a galaxy in a heartbeat of cosmic time. But inflation may not have ended everywhere at once. Instead, in some regions, expansion slowed, allowing energy to condense into matter and light, creating universes like ours. In other regions, inflation may have continued, driving space to swell faster than the speed of light. If this picture is true, then inflation is not a single event in the past. It is eternal, always bubbling, always creating. Each bubble is a universe, sealed off from the others by ever-expanding walls of space. Together, they form a multiverse, an infinite froth of realities, each with its own beginning, its own laws, its own story. Our own universe, then, would be just one bubble in this infinite cosmic foam. The constants of nature that we take for granted, the strength of gravity, the charge of the electron, the speed of light, may be different in other bubbles. Some universes might collapse in an instant. Others might expand forever, but without ever forming stars. A few may harbor galaxies, life, and intelligence. This radical idea reshapes the way we think about our place in existence. What we call the universe may be nothing more than a small patch of a far greater reality, like a single grain of sand on an endless shore. But the multiverse does not only arise from inflation, it also emerges from the mysteries of quantum mechanics, the strange rules governing the subatomic world. In the many-worlds interpretation, every time a quantum event occurs with multiple possible outcomes, the universe splits. A particle that could go left or right does both, in separate, parallel branches of reality. In one universe, you wake up and take one path. In another, you choose differently. According to this view, there isn't one universe with one history. There are countless universes branching endlessly, with every possibility realized somewhere. Taken together, eternal inflation and quantum many-worlds suggest a reality that is not only vast, but infinite. Not only infinite in space, but infinite in histories, in laws, in outcomes. A reality where everything that can happen does happen, somewhere. But if the multiverse exists, could we ever detect it? Could our universe bear scars of collisions with others? Some cosmologists believe so. If two bubble universes were to brush against one another during inflation, the collision could leave behind subtle imprints in the fabric of space-time, perhaps a circular pattern in the cosmic microwave background, the faint afterglow of the Big Bang. Scientists have searched for such patterns, but so far the evidence remains inconclusive. The universe keeps its secrets well. Yet, the search continues because if such a signature were found, it would be one of the most profound discoveries in human history, proof that we are not alone, not even at the level of universes themselves. The implications are staggering. If there are infinite universes, does our own truly matter? Are we just one story among endless others, destined to be repeated in infinite variations? Some see this as diminishing, reducing our significance to a mere statistical accident. But there is another way to see it. Perhaps what matters is not the uniqueness of our universe, but the fact that in this fleeting bubble of reality, consciousness has arisen. Stars have formed, life has evolved, and beings like us have begun to ask questions of the cosmos. Even if there are infinite universes, this one is the only one we can touch, the only one we can know. And that alone gives it meaning. The multiverse also deepens an old puzzle in physics, the question of why the laws of nature appear so finely tuned for life. Why is gravity so weak compared to the other forces? Why is the cosmological constant, the energy of empty space, so small, allowing galaxies to form? Why do the building blocks of matter hold together in just the right way to create atoms, molecules, and living beings? In a multiverse, the answer may be that these constants vary. We live in a universe that permits life, because only in such a universe could beings like us exist to ask the question. This is known as the anthropic principle, a controversial idea, but one that gains traction in a multiverse framework. Instead of being surprised that the universe allows us to exist, perhaps we should recognize that in universes where it didn't, no one would be there to notice. Still, some physicists push back. They argue that if the multiverse can explain anything, it explains nothing. If every possible outcome exists somewhere, then what predictions can we test? What makes one theory true and another false? It is here that cosmology begins to bleed into philosophy. The multiverse may be real, or it may simply be a mathematical mirage, but either way, it forces us to confront the limits of knowledge. How much of reality is forever beyond our reach? How far can human thought carry us into the infinite? And yet, the story of the multiverse does not end with despair. Instead, it reminds us of the profound mystery at the heart of existence. Whether or not other universes exist, the very possibility that they might reveal something extraordinary about the human spirit, that we can imagine beyond our bubble, that we can take the faintest hints, a pattern in the microwave background, a whisper in the equations, and weave them into visions of infinite reality, that we can look at the night sky and wonder not only what lies between the stars, but what lies beyond them, beyond everything we know. Perhaps we will one day find evidence of other universes, perhaps not. But in contemplating the multiverse, we glimpse a truth larger than the question itself. That the cosmos is not a puzzle to be solved once and for all, but a mirror reflecting back the boundless curiosity of those who dare to ask. And so the journey continues. From galaxies to dark matter, from inflation to the multiverse, we have seen the universe grow ever stranger, ever vaster. But there is one more question we must face, one that takes us not into parallel worlds, but into the deepest fabric of reality itself. For if the universe is expanding, if space and time themselves have a beginning, then what happens to the most fundamental thing of all, information? That is where we turn next. What is the universe really? Is it matter, stars and galaxies? Or is it something deeper, a vast web of information written into the fabric of space and time? As the universe expands, we usually think of galaxies drifting apart, of light stretching into red. But what if expansion is also the slow scattering of information itself, the dispersal of knowledge, memory, and identity across an ever-widening cosmos? This is where cosmology meets one of the strangest frontiers of physics, the idea that the universe is at its core not a thing, but a record. Physicists call this the holographic principle. It arose from studying black holes, those cosmic abysses where gravity crushes matter into a singularity. For years, black holes posed a paradox. When something falls inside, does its information vanish forever? According to quantum theory, information cannot be destroyed, but according to Einstein's general relativity, inside a black hole, it disappears into the singularity. The solution came from a startling realization. The information about everything that falls into a black hole is not lost but stored at its boundary, the event horizon, in the tiniest possible units, like pixels on a screen. This led to a radical proposal. Perhaps the entire universe works the same way. Perhaps the three-dimensional world we live in is a projection of information encoded on a two-dimensional boundary at the edge of space-time. The cosmos, then, is not just expanding matter and energy, it is expanding information. Think of expansion as not merely galaxies moving apart, but as patterns of information being stretched, fragmented, and dispersed. The light from a distant star is not just photons traveling through space, it is data, a record of nuclear reactions, of fusion of cosmic history. As the universe expands, those photons redshift, their information diluted across greater distances. In the far future, when expansion has carried most galaxies beyond our horizon, their information will be unreachable. The record of their existence will be scattered, unreadable, lost to us. Expansion is not just physical separation, it is the erosion of knowledge. But what does this mean for consciousness, for identity, for the fragile spark of awareness that wonders about its place in the cosmos? Quantum theory tells us that information is not passive, it is active, entangled, woven into the fabric of reality. Your mind, your memories, your sense of self are not separate from the universe's information. They are part of it, fleeting arrangements of matter and energy that momentarily give rise to thought. In a universe that expands forever, these patterns will eventually disperse too. Consciousness itself may be a temporary eddy in the cosmic flow, destined to dissolve back into the sea of expanding information. This is the paradox. The universe gives rise to beings capable of knowledge, yet the very expansion that allows galaxies and stars to exist also guarantees that knowledge will one day vanish. In the deepest future, as expansion accelerates, horizons will shrink, galaxies will fade into darkness, even the memory of them stored in the light they once emitted will be stretched beyond recognition. Civilizations could endure for trillions of years and yet still face the same limit, the erasure of the past, carried away by expansion. This is not just a scientific problem, but a philosophical one. If everything we know, every fact, every memory, every achievement is destined to be lost, what does it mean to know anything at all? Perhaps meaning does not lie in permanence, but in pattern, in the fleeting arrangement of atoms into a human being who looks up at the night sky, in the temporary gathering of galaxies into clusters,
before they drift apart, in the fragile spark of consciousness that, for a moment, illuminates the darkness. Meaning may not require eternity. It may exist precisely because of impermanence.
In this way, expansion becomes not just a cosmic fact, but a metaphor for existence. We are like galaxies, bound for a while, then separated by forces we cannot control. We are like photons, carrying records of our moments, stretched and scattered across time. We are information, temporary but real, etched briefly into the great unfolding hologram of the universe. To live, to know, to ask questions of the cosmos is to participate in this grand dispersal, to become part of the story of expansion itself. And so we return to the question with which we began. If the universe is expanding, what is it expanding into? Perhaps the answer is not a place, but a state, an ever-growing space of possibilities, a dispersal of information across the canvas of reality. Perhaps expansion is not into something else, but into deeper and deeper complexity, into patterns that rise and fade like waves on an infinite sea. In that sea we are not eternal, but for a time we shine. And this leads us to the final reflection. The universe is not only about what will be lost, it is also about what exists now, about the moment we are given, standing on a small planet, able to see, to wonder, to understand. The fate of information may be dispersal. The fate of knowledge may be forgetting. But the fate of meaning, that is something we create ourselves here and now in the fragile patterns of thought and connection we build. Perhaps that is the gift of an expanding universe. Not eternal certainty, but the chance to create significance in the face of impermanence. And so as we close this chapter, we step into the ultimate horizon, where science meets philosophy and cosmology becomes a mirror for human existence. Beyond expansion, beyond information, beyond the fate of galaxies and stars, lies the deepest question of all. Not just what the universe is, but what it means for us to be here at all. Look up at the night sky. What do you see? A canvas painted with galaxies, clusters, filaments stretching into infinity. A web of light that tells us the universe is alive, in motion, expanding. We know this because we can see the past. We can trace the red shift of galaxies. We can hear the fading echo of the cosmic microwave background. We live in a privileged time when the cosmos still reveals its history. But imagine standing on this same planet 150 billion years in the future. You raise your eyes to the heavens, and the sky is empty. No galaxies, no cosmic background radiation, no clue that the universe was ever anything but still. By then, cosmic expansion will have carried every galaxy beyond our horizon. Their light will have redshifted so far that no telescope could ever detect it. Even the cosmic microwave background, that faint afterglow of the Big Bang, will have stretched into wavelengths larger than the observable universe itself, fading into silence. All that will remain are the dying embers of our own galaxy, the stars that survive the long march of time, orbiting in a sky stripped of context. For those distant civilizations, if they exist, the universe will appear static, eternal, a quiet island of stars adrift in an endless void. They will look up and see only what surrounds them. And they will conclude, as humans once did, that the cosmos is timeless and unchanging. This realization carries a haunting question. Are we too deceived today? We take the expansion of the universe as fact. We trust our instruments, our telescopes, our equations. But so did the astronomers of earlier ages. For millennia the night sky looked fixed. The stars rose and set, but their patterns never shifted. The universe seemed eternal. It was only through deeper observation, through faint clues hiding in the light, that we uncovered the truth of expansion. If future civilizations will be blinded by absence, might we, in our own age, be blinded by presence? Do we truly see the whole story, or only the brief chapter, visible from our moment in time? The irony of expansion is that it hides its own beginning. The farther into the future we go, the less evidence remains. The story of cosmic birth and growth is not written for eternity. It is a tale that fades as time unfolds. And so we are left with the deepest paradox of all. If the universe is expanding, what is it expanding into? The instinct is to imagine a container, a larger space waiting outside the cosmos, into which galaxies spread. But physics tells us this is not so. There is no outside, space itself grows. The balloon does not expand into a room. The balloon is the room. Expansion creates the very arena in which it unfolds. The universe expands not into emptiness, but into itself. This idea is as unsettling as it is profound, because it forces us to abandon ordinary intuition. Every explosion, every swelling tide, every growing flame we know takes place in something. But the cosmos is not like that. It is not inside anything larger. Its growth is the growth of possibility itself. Each moment, expansion is not pushing into a void, but writing new chapters of reality, creating new space, new time, new conditions for what can exist. And so the true answer to the question may not be spatial at all. The universe expands into possibility, into new arrangements of matter, new horizons of complexity, new stories of life and awareness. But there is another way to see it. Perhaps the universe also expands into mystery, because with every discovery comes a deeper question. With every solved paradox, a new one emerges. We know the universe expands, yet we do not know why. We measure dark energy's repulsive push, yet we do not know its nature. We calculate p-far probabilities of cosmic futures, yet we do not know which awaits us. Expansion is not only physical but intellectual. It expands the realm of the unknown as much as the known. Each horizon we reach opens another beyond it, and in this sense the universe also expands into us. For we are not separate from this story, we are a consequence of it. Galaxies scattered by expansion became stars. Stars seeded the elements of life. Life became consciousness. Consciousness became curiosity. When we ask what the universe is expanding into, we are really asking about ourselves. Our role in this unfolding, our meaning in this immensity. And perhaps the answer is this: the universe expands into possibility, into mystery, into us, because we are the means by which it comes to know itself. So picture the night sky again, not as it is, but as it will be, an empty vault, silent and still. A future cosmos where the evidence of expansion has vanished. In that lonely sky, the truth will be hidden. But here, now, we stand at the intersection of light and time, when the universe still speaks. We are witnesses to a fleeting window of knowledge, the one moment in cosmic history when the evidence of beginning and becoming can be seen. And in this brief chapter, we are called to wonder, to reflect, to find meaning not in eternity, but in the mystery of expansion itself. For the universe expands not into space, not into void, but into the boundless realms of imagination and existence. It expands into possibility. It expands into mystery. It expands into us.